I'm going to continue with my series solving problems from the first chapter of Problem Solving Strategies by Arthur Engel. I've finished 42 out of 60 questions. The most recent few have been a mixture of pretty easy and really a lot harder than most of the preceding ones. And in 42 in particular, which was an old Maths Olympiad problem, took me, must have been about 2.5 hours or something in total, not all of which I was recording myself doing. As often with those harder problems, with hindsight, I look back and think maybe there were moments when I got bogged down in particular areas and should have unbogged myself, so to speak, quite a lot more quickly. And I could look again. Also, I eventually found an invariant that I needed by following the sort of method that I've been getting used to now for being rather systematic about developing invariants. So I got it in a systematic way. So why didn't I do that earlier on? Well, part of the reason was that I kind of guessed in a non-systematic way what it should look like based on an earlier problem that had an invariant that looked a little bit different, and ended up wasting quite a lot of time trying to tweak this invariant that was doomed not to work. So it was a fruitless exercise. So I want to try to avoid that kind of thing. I'm slightly also hoping that I'll get a little bit gentler problems for the next few, but we shall see. I can use a little bit also slightly, not exactly addicted, but I've been doing it as one of the first things I do each morning, a bit like Wordle, but much harder than Wordle. And for what it's worth, the last 3 days I've got Wordle in 3, so there. Right. So at least this next one doesn't actually say either that it's by some famous mathematician or that it came from some maths competition, so maybe I'll be okay about that. Let's see what it is. So number 43. 9 1x1 cells of a 10x10 square are infected. I have a horrible feeling this may be a problem that I've seen before and not solved, in which case this too is going to be difficult, but perhaps I can keep my head and make it not so difficult. In one time unit, the cells with at least 2 infected neighbours and it makes clear that, I won't bother writing it down, but a neighbour has to be horizontal or vertically next door, and it can't be diagonally, become infected. Can the infection spread to the whole square? Okay. Now, when I have some dim memory of trying to do this years ago, not trying all that hard, and not ever. I've certainly seen this problem before. Indeed, I think it's a favourite problem of my research supervisor, Bela Bolabash. So, how would an invariant work? Perhaps one would like to argue that we can add at most a certain amount to some quantity, and we would need to add too much to get to the whole square, but we know, so simple observation, if we just put 9 squares down a diagonal, we'll be able just to spread out from that diagonal with this infection. and fill up a 9 by 9 square, but that will leave out one row and one column. And my guess is that that's somehow the best that one can do. But what invariant would show that? So what invariant would distinguish? Now my systematic approach to this is always to say, well, let's at first just consider adding up, so associating all with each square in the grid some number and adding up all those numbers. It doesn't always work, but it's at least a good thing to try, and it reduces the search quite a lot. And there are some variants that one can take. So one can take these numbers that you put into the grid squares to be integers or real numbers or numbers mod something or other. And so there are a few options there. But if you want to be systematic, you can't just, you want to just guess. So one would like it to be an invariant. Now let's suppose we want it to be literally an invariant, something. So we either want it to be something that increases or decreases, or we want it to be something that stays constant. So I'm now going to think, what could I say if it always stayed constant? And the answer is, that's a bit of a disaster, because supposing I have A and B here, so in those grid squares, and this is an empty square, then I can put something in here, C, and if the sum of all these numbers remains invariant, that means C has to be 0. So an invariant of the kind, let's add everything up, and it should stay constant, is not very promising. So that means that I now want to turn my attention to things that increase, or maybe decrease. Maybe there's something like the number of edges available, or the number of corners or something goes down, or I think to get a feel for this, I might just have a look at a small case. So we've got a 10 by 10. What about a 3 by 3? So I'm going to get a proof that's absolutely not the sort of proof we're going to be able to end up with. So the only way of getting anything else infected apart from the initial 2 is going to be if the 2 are diagonally next to each other. But if the 2 are diagonally next to each other, let's not draw the grid at all, but if you have 2 things that are diagonally next to each other, then the best you can fill in is the 2 neighbouring things, and once you've done that, you've had it. Now, if something does seem to go down here, so in order to be able to fill in a square, you have to have a sort of what you might call an internal corner. And if I put an extra square in, I've lost an internal corner and gained an external corner. So that has gone down, but I don't think that's always going to go down. So for example, supposing I had 3 squares like that, how many internal corners have I got? I've got 1, 2. So by internal corner, I mean as I go around the boundary, I'm in an angle of 270 instead of 90, so to speak. But if I put this in here, I lose an internal corner. I lose an external corner, but I gain an internal corner, and I gain an external corner. But the next time, I lose one. And here I lose one, and then I'm stuck. So something looks as though it's going on there, but I need to count something a bit more, because if I've got a 180 degree angle there, that seems to help me So what about if I count the number of 270s and the number of 180s as I go round? Let's try that. So here, I'll just have a look at this example again. So here I preserved the number of 90s, I gained 180, I gained a 270. I've got to keep tabs of that. I sort of lost a 270, I gained a 270, I lost a 90, but I gained a 90, and I lost this 180, but I gained this 180. So that's still not very helpful. I seem to have gained exactly the same as I've lost. So what might conceivably have gone down? Why do I feel, so this is what I'm asking myself now. If I stare at these two pictures, picture 1 and picture 2, what has gone down? Why do I feel that this one is somehow sort of rounder than this one? And can I come up with some quantity that measures that sort of degree of, I've filled things up now and I can't fill any further? I would really... So could it be something like the length of the boundary versus the number of squares inside? Some sort of isoperimetric thing. So here I've got a boundary of length 4, 5, 6, 7, 8, 9, 10. And here I think the boundary is still going to be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But I've got 4 squares inside. So what about length of boundary minus number of squares? That's just something to look at. So can we argue that that's always going to go down, first of all? So if I've got a corner here somewhere, and I don't know what happens elsewhere, so it's sort of some stuff up here. When I put in a new square, that stops being boundary, and this becomes boundary, at least potentially. So I gain at most 2 boundary squares, lines, because I gain at most 2 lines at all. And I can't make something a boundary line that wasn't a boundary line before, apart from the 2 ones I introduced. I've removed 2, but I've added 1 to the number of squares. So that's kind of interesting. The length of the boundary minus the number of squares, or put it the other way around, number of squares minus length of boundary. What am I trying to say? What am I trying to say? It goes up by... Wait, what happens to the length of the boundary? The length of the boundary stays the same or goes down, but the number of squares goes up. Oh, but it's the length of the boundary that doesn't go up. So can it spread to the whole square? That looks as though that's the answer, because the boundary, if you've got 9 squares, has length at most 36. But the boundary, if you want 10 by 10, is 40. Is that it? So that's absolutely gorgeous if that's the answer. I wonder if everybody liked the problem. Let me just check that I'm not gone mad. I think I'm pretty sure I've solved the problem now, but I'm just doing 3 squares initially inside a 4 by 4. So the boundary initially has the maximum possible length of 12. And then as I start, I add this square. It's still got length 12 because I lost 2 and gained 2. I lose 2, gain 2, lose 2, gain 2, lose 2, gain 2, lose 2, gain 2, lose 2, gain 2. And I've got a 12 boundary around here, and I just can't make it into a boundary of length 16. Wow. Okay. So that was an old... It's quite nice actually to pick up a problem. I've got quite a few of those problems that people told me in the past. I had a little go and I felt a bit lazy, didn't solve them. And it's nice to put that into the solved box. And I'm also rather chuffed that it came out quite quickly, which suggests to me actually that now I really have gained something serious mathematically from this exercise of working through invariance problems, because I really did make an effort to be systematic then, and that effort paid off. I thought, could it be an invariant of such and such a kind? No, I'd better think about other things. Quite where so I had this thought about angles, but then I just had this feeling that something was sort of filling up and pushing up against the boundary. There was a point that is a little bit hard to pin down of why I eventually alighted on the right. So I hesitated there, should I say alit? But anyway, I alighted on the right invariant. Not quite sure what was going on. It did feel actually at the time like a sort of little bit of a leap. But anyway, I must move on. Enough post-mortem. Can you get the polynomial hx equals x? From the polynomials fx and gx. I presume the question will tell us what fx and gx are. Let's just check that. Oh yes, there'll be a different possibility. So by the operations, addition, subtraction, multiplication. So this is a very algebraic question. We're going to be asking what the subring or something like that generated by some polynomials is, and whether it contains x. If a fx equals x squared plus x, gx equals x squared plus 2, b fx equals 2x squared plus x, gx equals 2x, and c fx equals x squared plus x. Gosh, that's quite a lot to work on. Gx equals x squared minus 2. All right. Just addition, subtraction, and multiplication. So not multiplication by scalars or something. So we're in the world of integer polynomials. Now, an immediate observation is that if you have two polynomials that have a common root, then their sum has that root, their difference has that root, and their product has that root. However, I think in this case that doesn't do anything, because the roots, at least in question A, the roots are 0 and -1, and here the roots are plus or minus the square root of 2 times I, or something like that. Here I've got the roots 0 and -2, so they do have a common root of 0, but h has a root of 0 as well. And here we've got 0 and 1. So although having a common root would be an invariant, it's not going to be an invariant that helps us in this particular case. Although in part B, let me just quickly think about part B. So since everything's going to be a multiple of x, but the question doesn't quite, I can't just say I'll divide through by x, because when I multiply, that's going to get me away from x. So I'm going to go for A first of all. So an obvious thing to do first is some sort of Euclid's algorithm type thing, and just see what the highest common factor of these two polynomials is. So I can, if I subtract, so I'm just going to write down polynomials that are generated by x squared plus x and x squared plus 2. So I can certainly get x minus 2. And what can I do with that? If I square that, I get x squared minus 4x plus 4. Not quite sure why that was a great thing to do, but let's now see what happens if I wait. Is x minus 2 is not the highest common factor of those two, so but yes, it's not quite, I don't quite get enough to do Euclid's algorithm, because I can't multiply this by an arbitrary polynomial. I can only multiply it by polynomials that I've got around, so that's why I'm doing something like this. So x squared minus 4x plus 4, let's take this and subtract. And so x squared plus x minus this gives me 5x minus 4. And now I can get a multiple of x here. So if I take 2x minus 4, I can get, and then subtract it, I can get 3x. So I've managed to get 3x there. And is there anything? Let me just think, there's something else that is now beginning to strike me as a possibility. So although I don't seem to be able to use this, I've just made another observation, which is that if you look at the sum of the coefficients, which is just the value when x equals 1, if that's always a multiple of something, then when you add, subtract, or multiply the polynomials, that's also going to be an invariant. So another source of possible invariance is that some value of the polynomial is always a multiple of something or other. So actually, maybe just have a look at some small integers and see if I can argue that I get some value being always a multiple of something. So for example, if x is, I had this 3x, so perhaps what if x is, so I want x minus 2, to be some non-trivial thing. So perhaps I'd like x to be, say, 4 or something. That's not going to be interesting. X is 5, perhaps. So if x is 5, then x squared plus x is 30. And x squared plus 2 is 27. So those are both multiples of 3. In fact, because I've got this x minus 2 out of them, then I knew that as long as one of them was a multiple of 3. So if I look at f of 5, this is a trick question A, and g of 5, they are multiples of 3. So anything, if you can make h, let's just check that. If you add any two polynomials whose value at 5 is a multiple of 3, you'll still get a multiple of 3. And if you multiply, you'll still get a multiple of 3. So can't make h because hx equals x as h5 is 5, which is not a multiple of 3. Well, that's nice to know. I've managed to actually solve one. It's slightly scary though, because unless they're all like that, but so can we do anything similar for what can I get out of 2x squared plus x and 2x? So the 2x is going to tell me that the value at any point, the best that I can do is an extra factor of 2. But this one doesn't look as though it's going to get an extra factor of 2. So for example, if x is odd, that's going to be even, but this will be odd, so that won't help. If x is, let's just quickly check that this idea isn't going to work. So it isn't going to work. So I'm going to write x equals 2 to the a times b, where b is odd. Then here I will get 2 to the 2a b squared plus 2 to the a times b. The largest power of 2 that divides that is 2 to the a. And then here I get 2 to the a plus 1. So the best I can say is that the largest power of 2 that divides anything I can make is 2 to the a. So that will not distinguish h. So I'm hoping that means that I'll actually be able to make x out of these two, but it doesn't seem obvious to me. So let's just, if I take 2x and square it, I'll get 4x squared. Again, I'm writing down polynomials that I can make. And then 4x squared minus 2 of those. No, let's say 2 of those minus 4x, I can make 2x. Big deal. I knew I could make 2x. I can also make 2x squared minus x. So that is odd. I mean, odd in the sense of strange. Oh yes, let's just quickly think about, this was the one where we have a root of x. So actually I think something potentially interesting happens here. So let's just write this as x times 2x plus 1 and x times 2. Now if I ever multiply two polynomials together, I'm going to get a factor x squared. No, more than that. If I ever multiply two polynomials, yes, I'll get a factor x squared of the whole polynomial. And I want to say that I can't, that having polynomials that are multiples of x squared can't be of any use to me in some sense. I'll come back to that. It seems as though they won't be of much help. So can I argue that I can't generate x just as an integer combination of those two? Doesn't seem as though I can. So that's the same as saying I want to make x out of 2x plus 1 and 2. But I'm allowed, that's not, maybe I will also allow myself now I think this dividing through by x is not terribly helpful, because I obviously can't make 1 out of, as a linear combination, as an integer combination of those two. Why do I say that? Just because I can't get rid of this 2x, but then it's not true that I can't get rid of the 2x. So, because if I don't, because I do get to multiply this by something, so perhaps I can say 2x plus 1, 2, and 4x. Or maybe I should just consider the whole thing modulo x squared and see what happens there. So what do I get? What am I writing down? I'll just quickly rewrite the polynomials so I've got them. 2x plus squared plus x and 2x. So mod x squared, I so far have x and 2x. But that's not very useful. I'm not going to be able to show that I can't get x mod x squared because I've got x mod x squared. So there's something very peculiar happening. Okay, I wonder whether I should just look at C in case that helps. So x squared, I'll try C for the moment. And then come back to B. So x squared plus x and x squared minus 2. Can I please make x out of these? Or actually maybe I'll just quickly see whether there's an invariant that distinguishes them. That's going to be even always, and that's going to be even if and only if x is even, which is not very, maybe I want something else. I would like it to be, so x squared plus x mod something. That's not going to take. So that's x plus 1. So if x is, for example, 6 mod 7, this will be a multiple of 7. But x squared minus 2 won't necessarily be a multiple of 7. What's a square root of 2 mod something interesting? So 3 squared equals 2 mod 7. But 3 squared plus 3. But if x and minus 2 were the same thing, so but that would require minus 2 squared to be 2. That would require 4 to be 2, which would require 2 to be 0, which would require us to be just looking at parity. So I'm not getting something like the invariant that worked in the first place. So maybe this factorization is not very useful. Let us how can I ever get rid of this constant term here? It doesn't look easy. Actually, it's not too bad. So what if I square this? I get x squared, x to the fourth, I mean, minus 4x squared plus 4. And if I double this, I get 2x squared minus 4. And now I can add them together, get x to the fourth minus 2x squared. What if I multiply these? This is not looking very nice. But let's do it anyway. Multiplying those two together, I get x to the fourth plus x cubed minus 2x squared minus 2x. And if I subtract this, I get x cubed minus 2x. That's sort of interesting. What next? So the degree of this is even, the degree of this is even. If I add any two polynomials with even degree, I get something of even degree, but if I can subtract two polynomials of even degree and get something of odd degree, so that wasn't an invariant. But could there be something along those lines? Can I get another polynomial, another cubic? It looks difficult. There's a third quartic I could write down, which is x to the fourth plus 2x cubed plus x squared. If I subtract this from that, I get x cubed plus 3x squared plus 2x, if I'm not much mistaken. Let's just check that. This minus this, x to the fourth, 2x cubed. What was I doing? I think I had this, I subtracted that. Oh yes, 2x cubed minus x cubed gave me x cubed. X squared minus 2x squared gave me 3x squared. 0 minus 2x gave me 2x. So now it's tempting to subtract this, and I get 3x squared plus 4x. So I've got a third quadratic in there. Maybe I can simplify that a little bit by just subtracting 3 of those, which gives me x. So I can make x in that case. So now back to b. The initial polynomials were 2x squared plus x and 2x. I'm seeking an invariant. What could the invariant be like? It seems very striking that everything I get is going to be a multiple of x. So let's just think about what happens if I take xpx and xqx. So I'm always going to get, I can get x times px plus or minus qx, and I can get x squared times px qx. But x squared times px qx doesn't feel as though it's all that helpful. But I've not actually managed to explain why I feel that's not helpful. So let me, in an effort to do that, let's just think, what is the set of polynomials? If you've got two polynomials p and q, what is the set of things that you can make out of p and q by addition and subtraction and multiplication? Is there some general form that I can write down? I think there is. I think I can make an arbitrary polynomial with integer coefficients out of p and q. Indeed, I certainly can make any such polynomial, because I can take any power, I can get any power of p, and I can multiply that by any integer, positive or negative. Actually, maybe not straight away. I can't sort of say I get minus 2x, but I can always sort of add minus 2x. So I'm not saying I can actually make that itself, but I can, in combination with other things, I can make it. And similarly, I can make BL q to the L, and I can multiply those together. AK BL p to the k q to the L. So I think basically I'm going to think about polynomials in those polynomials. And now I want to argue that those polynomials must be in some sense not involving, well, they mustn't involve x squared, so everything has to cancel, but how much stuff is there to cancel? That's what a little bit. Also, if p and q both have factors of x, then I can let p equal x r and q equals xs. So this becomes ak x to the k r to the k and bl x to the l s to the l. And so I need somehow to argue that a whole lot of stuff cancels out to have any chance of getting x. Now, could it be that, no, because when I square that, I thought there might be some parity thing about the polynomial that's beyond the, from x squared and onwards. So for example, 2x squared plus x squared would be 4x to the 4 plus 4x cubed plus x squared, and from 2x I can get 4x squared. I can also get 8x cubed. I can also get 16x to the 4th. So now I could subtract 4 of those well, let me just, I can turn that into a 16. And this 4x squared, what could I turn that into? So I'm going to multiply 4 of those. But I've got myself a multiple of 4x to the fourth plus 4x cubed plus x squared. But if I were to multiply this by 2 or something to get 8x squared, then when I subtracted 4 of these, I'd have 4x squared, but I had the 4x squared already. So 4x squared seems to be playing a role here. But what role? Because I certainly don't, I can't say that the x squared part is always a multiple of 4, because that's not true. But let's just think about the value. Somehow it seems as though powers of 2 are relevant in some way, although I thought I'd also sort of established that they were not terribly relevant. But if I think about this in its binary thing, I've got 1, 0. I'm just looking at the value that it takes at 2. Actually, it's 1, 0, 0. And then this one takes the value. Well, that's why use binary? Let's just, so that one takes the value 4. And here, the value taken at 2 is 8 plus 2, which is 10. So in theory, we can certainly find a polynomial that takes the value 2 at 2 by just subtracting 2 of those. So I can get 2x squared minus 3x. So when x equals 2, I've got 8 minus 6. But why doesn't that? Maybe I should be looking at something clever like the value taken at some rational number, which seems a bit silly, but what about the value taken as a half or something? Or even the value taken at minus a half. So if I take the value at minus a half, it'll be 0 here, and here it'll be minus 1. So the value at minus a half is an integer for both of those polynomials. If I take any integer combination of those two, then obviously the value at minus a half will be an integer. And if I multiply them, the value at minus a half will be an integer. So my invariant was the value at minus a half, which came as a big surprise to me because I was talking about integer polynomials, and I stupidly didn't think, well, actually I could actually look at values at places that aren't integers. What was it that provoked that? It was a repeated failure to get anywhere with values at integers, and yet a feeling that somehow that wasn't completely the wrong thing to look at. And with hindsight, I can then rationalize this decision quite well, because I can say I'm looking at these two have a common root, mod 1. So this has a root minus a half, mod 1. This also has a root minus a half, mod 1. And although integers mod 1 sorry, real numbers mod 1, let's say, or rationals mod 1, don't form a field. They do form enough of a nice structure. I don't want to say something stupid, but I think they probably form some ring or something or other. That general idea of common roots actually works for that case. And actually we can look at A in the same light. F5 and G5 multiples of 3, that's just saying mod 3, these two polynomials have a common root. So actually to F2 and G2, they're both multiples of 3, 6, and 6. Yes, I could have taken F of 2 and G of 2 mod 3. So now I've gained a bit of a slightly better theoretical understanding of what's going on in that question. So that took me a bit of time, and I think enough time that I should stop for this video, stop for today. But I'm really quite happy to have done this problem about the infecting squares, and I'm quite happy actually to have puzzled through number 44 on polynomials. So the problems do seem to be still, on average, a little bit harder, but those two weren't as hard as the ones I did yesterday and in the preceding couple of days. So thank you very much.